Welcome everyone. I'm excited to welcome you to today's presentation. Today we'll be exploring building materials. This is the first slide, so I just want to briefly introduce what we'll be covering. We'll look at different types of materials used in construction, their properties, and how they impact building design. I promise it will be an informative session, so let's get started. When selecting a good building stone, there are several key requirements to keep in mind. First and foremost, the stone must be strong against crushing, which means it needs to have high compressive strength to bear loads without breaking. Durability is also essential, especially in outdoor environments where weather conditions can cause deterioration over time. A good stone should fracture cleanly, with sharp, well-defined edges, and be free from loose grains, ensuring a neat appearance and structural integrity. It also needs to withstand abrasive actions, like wear from friction or contact with other materials. For underwater construction, heavy stones are preferable because they stay in place and resist buoyancy. Proper compaction during quarrying or placement ensures stability. Fine grain structure and low porosity are important because they reduce water absorption, making the stone less susceptible to damage from freeze-thaw cycles or moisture. Ease of dressing is another critical factor, as it affects how easily the stone can be shaped and finished on site. Fire resistance is vital, especially in structures exposed to high temperatures. And of course, aesthetic qualities matter for visible surfaces, where appearance can enhance the overall design. All these factors, strength, durability, workability, and appearance, tie into the overall theme of selecting the most suitable stone for durable, safe, and visually appealing structures. Let's talk about lime today. Lime is primarily composed of calcium carbonate along with some impurities. It plays a crucial role as a cementing material in construction. For example, lime is often used in whitewashing to give walls a bright, clean look. It's also essential when embedding tiles on roofs and floors, helping them adhere securely. Additionally, lime is used in preparing plastic mortar, which is versatile for various building applications. Another important use is in plastering, where it helps create smooth, durable surfaces. Overall, lime is a fundamental material that supports many building and finishing processes, tying into the broader theme of construction materials and their vital functions. Let's discuss the classification of lime. First, we have quicklime, which is derived from seashells, coral stones, and limestone. When you add water to quicklime, it slakes, meaning it reacts with water, expanding to about 2 to 3 times its volume. This process causes it to shrink and crack as it dries. Quicklime sets by exposure to air and water, making it useful for applications like plastering, painting, and whitewashing. On the other hand, we have hydraulic lime, which is made from limestone combined with clay and magnesium carbonate. Unlike quicklime, hydraulic lime slakes without much heat or significant increase in volume, and it experiences less shrinkage during setting. Importantly, hydraulic lime hardens and sets through a chemical process, making it suitable for building construction where stronger, more durable material is needed. Understanding these differences helps us select the right type of lime for specific construction purposes, ensuring both strength and workability in our projects. Let's talk about manufacturing, specifically the burning or calcining process. This involves heating calcium carbonate, which is CaCO3, to produce quicklime, CaO, along with carbon dioxide, CO2. When we burn the limestone, it decomposes into calcium oxide, or quicklime, releasing CO2. Once we have the quicklime, it's often mixed with water to produce slaked lime, known as calcium hydroxide, CaO2. This process of hardening or setting is essential in many construction and industrial applications. Now, regarding burning methods, there are a few key techniques. One is the clamp method, where layers of limestone about 5 to 8 centimeters thick are alternated with fuel and covered with clay. This creates a sort of makeshift kiln, with lime and ash playing a role in the process. Then there's the continuous kiln, which is more advanced. Here, limestone and fuel are fed alternately, and additional limestone is added from the top as the process continues. This setup allows for a steady, ongoing production. The intermittent kiln is another option, often circular, about 2 meters in diameter and height, built with mud walls roughly 30 centimeters thick. It involves layers of straw, wood, broken limestone, and mud on top. This kiln is usually used in smaller-scale operations and requires a storage period of about 2 to 3 months for the material to mature. Finally, storage of the lime is also critical. It needs to be kept in closed spaces, either covered heaps with mud, airtight vessels, or even gunny bags, to prevent moisture absorption and maintain quality until it's needed. All these methods and storage techniques are key to producing high-quality lime efficiently and safely, fitting into the larger picture of manufacturing and construction. Today, I'll be talking about different types of sand and their unique characteristics. First, let's look at pit sand, which is also known as road sand. This type of sand is typically obtained from digging grounds or quarries, often from old alluvial soils. It has sharp, angular grains, mainly because it contains iron oxide, giving it that distinctive rough touch. These sands also include silica, mica, and clay, which are all affected by atmospheric conditions. Next, we have river sand, which is used mainly for plaster and mortar. River sand is deposited along riverbeds, so these grains tend to be less rounded compared to sea or beach sands because they haven't been rolled around as much. It's mostly free from clay and silica, which means it offers less adhesion, making it suitable for certain construction applications where a smoother finish is desired. Finally, sea sand, found along the coast and underwater, has a different set of properties. The grains are more rounded due to constant wave action, and they often contain alkaline salts. This type of sand is known for attracting moisture, which can sometimes be a challenge in construction. To make sea sand usable, it's typically treated with sulfuric acid to remove the salts and prevent issues like corrosion. Understanding these differences is crucial because the choice of sand can significantly impact the strength and durability of construction materials. Each type has its specific uses, and knowing their properties helps us select the right one for different projects. Let's start by looking at the classification of sand based on particle size. Fine sand passes through a 1 mesh, which makes it suitable for plaster. Coarse sand ranges from 1 to 3 and is typically used in mortar. Gravel, which ranges from 3 to 6, is used in concrete and often contains pebbles and other larger particles. Now, moving on to the properties of good sand. These are crucial for ensuring quality in construction. First, general characteristics include being sharp, clean, coarse, and mineral-rich, with minimal voids and primarily silica-based. Sharpness is important because it enhances the adhesion of cement and improves resistance to sliding. Fineness also plays a key role. Coarser sand tends to produce stronger mortar, but mixing coarse and fine sand can give better results overall. Durability of the sand improves when the right mix is used. Fine sand generally provides better mortar strength, but it's all about balancing the mix. Next, let's talk about voids. Good quality sand typically has voids around 40%, which affects workability and strength. Bulking, or moisture absorption, is about 4% of moisture content, and this impacts how we handle and mix the sand. Additionally, we can use substitutes such as ground brick, tiles, or rock dust, especially when natural sand is scarce or to achieve specific properties. Understanding these points helps us select the right type of sand for each application, ensuring the durability and strength of our structures. Let's talk about cirque and cement. Cirque is essentially crushed bricks. These are clay bricks that have been burnt and ground into a powder. When we look at types of cirque, well-burnt bricks are the most common. Cirque, on the other hand, is an inert body, meaning it doesn't react chemically, and it can be used as a substitute for sand in various applications. Half-burnt bricks are also used to add with fat to form hydraulic mortar, which is important because it hardens in the presence of water. However, we should be aware that exposure to the atmosphere can limit the effectiveness of cirque, especially if it's not properly handled or stored. Now, brick sand is a mixture of well-burnt bricks combined with lime mortar. It's used as a substitute for natural sand when mixing with cement, and this creates a fairly good mortar. As for proportions, a common mix is 1 lime to 1 cirque, or 1 lime to 2 cirque. For a more balanced mix, you can go with 1 lime, 1 Sirke, and 1 sand. Understanding these materials and their proportions helps us improve the durability and strength of our construction, aligning with the overall goal of building better, more sustainable structures. Cement is a calcareous binding material that plays a crucial role in construction. It has rich hydraulic properties, which means it can set and harden underwater, making it very versatile. When compared to lime, cement is superior because it offers higher strength and faster setting times. This makes it ideal for projects that require quick turnaround. Cement also creates watertight structures, ensuring durability and resistance to moisture. Its hardness and durability mean that structures built with cement can last for decades with minimal maintenance. Additionally, cement is often used for plastering surfaces that will be painted, providing a smooth, strong finish. Overall, cement's combination of strength, quick setting, and water resistance makes it an essential material in modern construction. Now let's look at the manufacturing process. First, limestone is crushed in silos to prepare it for the next steps. Then it goes into a wet grinding mill where it's ground into a fine powder. At the same time, we add a wet clay mixture, known as slurry, to this limestone. This slurry is then fed into a kiln. The kiln itself is a cylindrical chamber with an outer steel shell, usually between 2 to 5 meters in diameter, and it rotates on its axis. This rotation ensures even heating and mixing. The kiln is heated by crushed coal, which provides the necessary energy for the process. As the slurry moves through the kiln, it undergoes a chemical transformation and turns into clinker, which are small, hardened nodules. After cooling, the clinker is sent to a ball mill, where it's ground into a fine powder. This is the cement we use. This process is crucial because it transforms raw materials into the final product through a series of carefully controlled steps, highlighting the importance of each stage in producing high-quality cement. Let's take a closer look at the properties of cement. First, chemical composition is crucial because it determines how the cement behaves and sets. Then, we have fineness, which affects the rate of hydration and strength development. Thoroughness refers to how well the cement particles are ground. Finer cement reacts faster. The level of burning during manufacturing can influence properties like setting time and strength. When water is added, cement undergoes a 2-stage stiffening process. The initial set is when the material begins to harden but can still be disturbed without damage. The final set occurs when it becomes more rigid and is liable to break if disturbed. Hardening is the process of gaining strength over time. An important aspect is heat evolution, which occurs during hydration. This releases heat as the cement reacts with water, impacting the curing process and structural integrity. Understanding these properties helps us control the quality and performance of cement in construction. Let's talk about the cement characters, which are quite important for understanding the quality and performance of our concrete. First, the color of cement should be either gray or a greenish gray. This is a key indicator of its composition and quality. Next, specific gravity is an important property. It should range between 3.15 and 3.19. This tells us about the density and the quality of the cement particles. When it comes to fineness, cement should pass through a 72 by 72 sieve with only about 10% residue remaining. This fineness influences the rate of hydration and strength development. Additionally, the weight of a standard 50-kilogram bag of cement should be about 1.4 kilograms per cubic decimeter. This ensures consistency in mixing and quality control. Now, moving on to the structural behavior of cement. Ideally, it neither expands nor shrinks significantly, which helps prevent structural distortions. Excessive expansion or shrinkage can lead to problems like cracking of plaster or even rumbling of the structure over time. Regarding setting time, initial set occurs roughly around 30 minutes under medium heat conditions. This indicates how quickly the cement begins to harden after mixing. The time taken to develop working strength is also crucial. It determines how long you can work with the concrete before it becomes too stiff. However, it's important to note that cement with these characteristics generally has low resistance to chemical reactions, which can be a concern in aggressive environments. So, understanding these key cement properties helps us select the right type for our specific construction needs, ensuring durability and structural integrity. Let's talk about rapid hardening cement. As the name suggests, this type of cement sets much faster than traditional cement, making it ideal for situations where quick strength development is needed. It's characterized by a faster rate of hardening, which is achieved through the use of finely ground materials. The finer particles accelerate the hydration process, leading to quicker strength gain. Additionally, calcium chloride is often added to further speed up the setting time. When we look at its properties, the initial set occurs in about 25 to 30 minutes, which is significantly faster than regular cement. The final set happens in approximately 9 to 10 hours, allowing for rapid construction schedules. This rapid development rate means that in just about 7 days, you can expect high early strength, which is crucial in some projects. However, it's important to note that this fast setting process also leads to high heat evolution during hydration. While this can be advantageous in cold weather, it also means the cement might have low resistance to chemical reactions over time, which can affect durability in aggressive environments. Overall, rapid hardening cement is a powerful tool when quick results are needed, but it requires careful consideration of its heat and chemical resistance properties to ensure it's suitable for your specific application. High alumina cement, as the name suggests, is rich in alumina, which gives it some unique properties. It's made from a mixture of limestone and bauxite, and the key here is that it has a higher proportion of alumina compared to ordinary cements. This special composition makes it particularly useful for specific applications. For instance, it's highly valued in fire-resistant concrete because it can withstand extreme heat. Another important point is that high alumina cement is immune to seawater, making it ideal for marine structures. Now, when it comes to setting time, it's quite peculiar. It sets relatively quickly, taking about 2 to 6 hours initially, with a final set in roughly 4 to 8 hours. This rapid development means that within just 24 hours, it can reach a workable strength, which is quite impressive. However, this fast rate of development also means it releases heat very quickly during curing, which can be a concern. The heat of evolution is high, so proper management is necessary to avoid issues like cracking. Interestingly, despite this rapid setting and heat release, high alumina cement is highly resistant to cracking, adding to its durability. Overall, these characteristics make high alumina cement a specialized material, especially suited for projects demanding fire resistance, marine resistance, and quick strength development. It's a great example of how understanding the properties of different cements can help us choose the right one for specific needs. Now, let's talk about quick setting cement. As the name suggests, this type of cement sets very rapidly, making it ideal for situations where time is of the essence. Typically, the initial set occurs in about 20 minutes, which is remarkably fast compared to regular cement. The rate of development during this period is very rapid, so it gains strength quickly, allowing for faster project completion. However, because it develops heat during setting, the heat generated can be quite high, which is an important factor to consider during application. Also, quick setting cement tends to have lower resistance to chemical action, meaning it might not be suitable for environments exposed to aggressive chemicals. Now, regarding the options for coloring, colored cement usually contains about 5 to 10% pigment, which provides vibrant and durable colors. On the other hand, white cement is of high quality and free from iron, making it ideal for applications where a pure, bright finish is desired. Overall, quick setting cement is a powerful tool for fast-paced projects, but it's important to weigh its rapid setting properties against potential limitations like heat generation and chemical resistance. Now, let's talk about storage, which is a crucial aspect of proper material handling. First, setting and hardening are important because materials need to be stored in a way that allows them to set or harden properly before use. Next, we should aim for a short storage period to prevent deterioration or damage over time. Damp proofing is essential to protect materials from moisture, but it's important to note that storage should not be against walls, as this can hinder air circulation and lead to dampness. Additionally, there should be no circulation of air around stored materials, which might sound counterintuitive, but in certain cases, it helps prevent dust and dirt from settling. To further protect the materials, using a damp-proof platform is recommended, which creates a barrier against ground moisture. Overall, these points emphasize that proper storage conditions are vital to maintaining the quality and integrity of materials throughout the construction process. Let's talk about mortar. Essentially, it's a mixture of lime or cement combined with sand, and it's in a plastic state, meaning it's workable and easy to apply. Now, why do we add sand? Well, sand helps prevent shrinkage as the mortar dries, adds strength, increases the bulk, and improves how it sets. Plus, it helps subdivide the paste and kickstarts the chemical reaction necessary for setting and hardening. When we consider the mechanical mixture, we're talking about combining a cementing material, like cement or lime, with inert materials such as sand. The proportions of these components can vary depending on what we need, whether that's more strength, better bonding, or specific workability. For hydraulic lime, the typical mix ratio is about 1:1 with sand, which means equal parts. Fat lime, on the other hand, is usually mixed at around 1:3, so more lime relative to sand. When working with cement and sand, common ratios range from 1:2 up to 1:6, depending on the desired strength and workability. Ultimately, these proportions are not fixed. They can be adjusted based on the specific requirements of the project, such as strength, positioning, and the binding material used. Understanding these variations helps us create the right mortar for each application, ensuring durability and performance in our constructions. Let's take a closer look at the various functions of these materials. First, they act as a plastic uniform on brick, stone, and metal surfaces, providing a smooth, consistent layer that helps improve the overall appearance and finish. This uniformity is crucial for achieving a professional look in construction and repair work. Next, they serve as an adhesive cementing material, meaning they help bond different surfaces securely together. This adhesion is vital for structural integrity and durability, ensuring that the components stay firmly in place over time. They also function as a hard, smooth covering, which not only enhances the aesthetic appeal, but also offers a protective barrier against environmental factors like moisture and wear. Additionally, these materials facilitate molding, allowing us to shape and form them into specific designs or contours as needed for various applications. They are also used for filling up joints, which is important for sealing gaps and preventing issues like water infiltration or air leakage. Overall, these functions highlight the versatility and importance of these materials in construction, repair, and finishing processes, connecting directly to our goal of achieving durable, attractive, and well-constructed structures. Now, let's talk about the preparation of mortar. The first step involves using a mortar mill or pan mill. This equipment helps us crush unslaked lime to ensure it's properly processed. Next, we need to mix inert material into the lime, which improves the mortar's properties and workability. This process of amalgamation can be done either by hand or with machinery, depending on the scale of the project. For masonry work, the typical mortar requirement is about 0.3 cubic meters per cubic meter of masonry. For brickwork, it's slightly less, around 0.25 cubic meters per cubic meter. Remember, cement plays a crucial role here. It fills the voids in the sand, making the mortar stronger and more durable. Overall, preparing mortar correctly is vital because it directly influences the strength and longevity of the structure. Proper mixing and proportions ensure that the mortar performs well under different conditions, contributing to the overall stability of the building. Let's take a closer look at some traditional mortar preparations. First, we have mud mortar, which is quite common in historic construction. It typically starts with stiff clay and ground material. The ground is prepared by removing coarse impurities to ensure a smoother mixture. Once that's done, the clay and ground material are mixed thoroughly with water to create a workable mortar. To prevent shrinkage and cracking, chopped straw is often added, This acts as a reinforcing material. This type of mortar is generally used for inferior and cheaper work, where cost and simplicity are more important than durability. Understanding these materials helps us appreciate the evolution of building techniques and the choices made based on available resources and intended longevity. Let's talk about lime mortar, a traditional and effective binding material. It mainly consists of lime, sand, and water. The key is to provide an even bedding, which ensures good adhesion and stability. Lime mortar acts as an adhesive material, holding the bricks or stones securely in place. The lime used here can be hydraulic lime, which sets underwater, or fat lime combined with surkey, a type of crushed brick or terracotta. When mixing for general purposes, the proportion is typically 1 part concrete to 2 parts sand. For plastering, we do it in 3 coats. The first coat is mixed at a 1:2 ratio of lime to sand, the second coat at 1:1, and the third at 2:1. This layering helps achieve a smooth, durable surface. Pointing, which is the finishing of joints between bricks or stones, uses a mix of hydraulic lime at 1:2, fat lime at 1:1/2, surkey at 1:2, and sand. This ensures flexibility and longevity in the joints. For terraces, the mixture is slightly different. Hydraulic lime at 1:2, fat lime at 1:1/2, surkey at 1:2, and sand. This helps withstand exposure to weather and temperature changes. Overall, understanding these proportions and applications is crucial for creating durable, breathable, and environmentally friendly masonry work. Cement mortar is a fundamental material commonly used in construction, and understanding its proper preparation is crucial for quality work. When preparing cement mortar, the first thing to consider is water. It should be free of any impurities like saturated oils or other contaminants that could weaken the mixture. Next, we need cement, which should not be set or hardened before mixing. The sand used from the river must be free of dirt and other impurities to ensure a strong, durable mortar. The process involves creating a heaping, or a depression in the mixture to add water. Only the required amount of water should be added to achieve the right consistency. When mixing, the ratios are very important because they determine the strength and use of the mortar. For example, a standard ordinary mix is 1 part cement to 6 parts sand, while a light mortar mix is 1:3. For plastering, a 1:5 ratio is common, and for tight wall plastering, a 1:3 mix works well. Pointing typically uses a 1:4 ratio, and terracing might use 1:3. For repairs, a stronger mix like 1:2 is often used, and for arches, a 1:1 ratio, which is more cement-heavy, provides the necessary strength. Waterproofing mortar is usually made with pure cement to ensure it's waterproof. The key takeaway here is that adjusting the ratios based on the specific application is vital for achieving the desired strength and durability of the mortar, which ultimately impacts the quality of the construction. Let's talk about concrete. Essentially, it's a paste made from binding material, water, and coarse aggregates that harden over time through a chemical process. When it sets, it becomes as hard as rock, which is why it's such a fundamental building material. Now, in terms of composition, the key elements are the binding material, which is usually cement, and the aggregates. The cement provides the bonding and tensile strength, and we typically use a high proportion of ordinary cement by weight to ensure good bonding. The aggregates are used mainly to fill the voids in the mixture, giving the concrete its bulk and strength. We include fine aggregates, like sand, to increase the mass and reduce costs. For example, about 10% of the fine material should pass through a 100 mesh sieve, which helps in creating a smooth, workable mix. When selecting sand, we prefer river sand or sea sand, but it's important to clean them thoroughly before use to remove impurities. Cleaned sand ensures the concrete's strength and durability are maintained. Overall, understanding the composition of concrete helps us design mixes that are both strong and cost-effective, aligning with our goal of building sustainable and durable structures. Let's go over the testing methods for soil analysis. First, for silt and clay, we use a simple jar test. You fill a jar with a known volume of soil, typically half filled, Then add water up to 3/4 of the jar. Shake it well and let it settle for about an hour. If the deposit at the bottom is about 1/17 of the total volume, it indicates the soil is unfit for certain uses. This helps us understand the fine particle content. Next, for the sample testing, we heat the soil to around 110 degrees Celsius for about 15 seconds, then add water and allow it to settle and filter. The key here is that the loss in weight shouldn't exceed 5%. This process helps us determine the organic matter content by measuring the weight loss after burning off the organic material. Now, regarding organic matter, we take a sample and fill a bottle about 1/3 full, then add a solution of 3% NaOH up to 2/3 full. After settling for 24 hours, the color indicates the organic content. A muddy color suggests high organic matter. A light beer-like color indicates moderate levels. A golden hue shows low organic matter. And if it's absent, it means very little or none is present. These tests are essential because they give us vital information about soil composition and fertility, which directly impacts how we manage and utilize the land.